And good morning, everyone. I'm Andrea Ticozzi, and today I will present our work on fast and efficient smooth polynomial lane change generation for high-speed autonomous driving. So, as it's clear from the title, we will propose a method for a polynomial lane change planning, which main focus will be on ensuring trajectory smoothness. That, as we will see better later, it's a paramount requirement for safe drivability at high speeds. At the same time, we will be able to show that the proposed method is able to efficiently guarantee compliance with track or road bounds for any kind of lane change maneuver. So we obviously must start from state-of-the-art approaches in the field of primitive-based path planning, where we can distinguish two main classes. The first one is uses parametric curves to design the lane change trajectory, and this kind of approaches are well suited to generate smooth lane change segments, given that we choose a proper parametric curve. But in some cases, as we will see better later, smoothness at the merging point, so at the beginning or the end of the lane change maneuver, is not always guaranteed. On the other hand, curvature-based methods are better suited to generate smooth segments also at the merging points, but are less suited to impose positional constraints on the lane change coordinates, so to easily ensure compliance with any track or road bound. So before going in the details of the proposed method, we must make a few remarks and a few introductory steps. So first of all, we want to underline what we mean with path smoothness. From now on, we will use path smoothness to indicate continuity in position, heading, and curvature for a certain path. Now we will try to understand why path smoothness is so important. First of all, we can consider a simple vehicle model as the bicycle model, in which we immediately see that the curvature is directly linked to the steering angle. So if we want to have a feasible steering dynamics, so if we want to impose that the steering derivative will be bounded, we need to require the curvature to be continuous. On the other hand, if we consider a rather popular control framework for autonomous driving, we can see that in such frameworks, a planner produces references for a trajectory tracker. So in such architectures, it's rather usual to use the reference trajectory curvature to compute the feedback or feed-forward steering commands. So under this consideration, we can understand that a smooth path, so a continuous curvature, will hide smooth control actions. And it's again very important for safe drivability at high speeds. After this introduction on why smoothness is so important, we must underline what we used as a framework to develop our approach. It's the rather popular in the planning algorithm. It's the rather popular Darboux reference system, in which we can represent any path in terms of lateral displacement with respect to a given base path that is usually the center line or the inner line of our track or our road. In such representation, we can link heading, curvature, and n coordinate and its derivatives of any path with these relations here. So after this formulation, we can consider a rather popular method for generating lane change trajectories that we used as a benchmark and a starting point for the solution we will propose later. With such methods, the n-coordinate profile of the lane change trajectory is defined as a fifth-order polynomial in which the coefficients of the polynomial are computed by imposing merging smoothness at the merging points. So as we see here, and if we consider the equations showed before, we can understand that if the base, origin, and target paths are represented as sets of discrete points, we will need to numerically differentiate path variables to impose these conditions. So with all the problems and noise introduced by numerical differentiation, in practice, in some cases, we're not able to perfectly guarantee smoothness at the merging points. For this reason, we propose a novel method that tries to overcome this limitation. In particular, we start also in this case from the popular Darboux reference system, and we define in this case the n-coordinate profile of the lane change trajectory as the convex combination of the n-coordinate profiles of the origin and target paths. The coefficient of the convex combination is varied throughout the lane change by means of a morphing function alpha, and where the morphing function alpha during the lane change is a fifth-order polynomial. So based on this formulation and on the equations we showed before, we can impose, to compute the polynomial coefficient, we again impose smoothness at the merging points, but in this case, the system that we obtain is much simpler, and its solution, it's showed down here in closed form, and as we can see, it only depends on lane change length and doesn't require in any case to compute any numerical derivative of path coordinates. At the same time, we can use the intrinsic convexity properties of the developed solution to show an important result. If we assume that the origin and target paths are feasible, so basically they lay inside the track, we can easily conclude that the lane change profile will always lay in between the origin and target paths, and so will always be feasible a priori. So this can be guaranteed for any lane change segment, and is very efficient in terms of we don't need to check the lane change segment after we generate to be sure that it's going to be feasible with respect to track bounds. We can now show the main results we obtain with the proposed solution and compare them with the benchmark solution we showed before. So the first scenario is a lane change at the curve entry, in which we can easily see that the benchmark solution, due to the fact it's affected by numerical differentiation of discrete path coordinates, it's showing a relevant discontinuity in the curvature profile at the end point of the lane change segment. On the other hand, the proposed solution is perfectly smooth and continues in its curvature profile. We simulated these two trajectories on a racing simulation environment, and without going into the details of the employed simulated model and in the control architecture, we just need to say that the controller uses curvature references to compute steering angle. So as we anticipated, in these cases, a non-smooth reference trajectory is detrimental both for comfort and stability. So we see that with the benchmark solution, we have big oscillations both in the steering and in the yaw rate profiles, while the morphing solution is perfectly smooth on both profiles. The second results we show is another lane change scenario, this time on a curve much closer to the track bounds. We can easily see that the benchmark solution violates the track bounds by more than half a meter, while the proposed morphing solution lays always in between the origin and target paths, so it's always feasible. This results allow us to say that this method is efficient because there's no need of checking the generated lane change segment after the computation, because we are always sure that the segment will be inside the track bounds for any kind of lane change from and to feasible trajectories. We can now draw the main conclusions of the proposed method, and we must say that we started from state-of-the-art approaches where lane change planning is a definitely popular topic, and we considered a benchmark algorithm in which lane changes are defined as fifth-order polynomials in the Darboux reference system. In such benchmark method, we noticed that there's some problems in imposing perfect smoothness at the endpoints of the lane change segment if we use discretized path representation, so sets of sampled points in the Cartesian or Darboux reference per frame. Also, for this kind of approaches, track bound compliance cannot always be guaranteed a priori for any kind of lane change. For this reason, we tried to overcome these limitations by developing a method that is again based on Darboux reference frame and on fifth order polynomials, but as main idea, the fact that we're realizing a convex combination of origin and target paths. And this allows to always fast and efficiently generate smooth lane change segments also at the endpoints without the need of numerically differentiate path variables, and also to efficiently guarantee that the generated segment is always compliant with track bounds. So this concludes the presentation. Thank you for your attention. And I think I have to leave the stage to my colleague Rodrigo now.
Yeah, thank you very much. And
thank you.
Cheering from virtually cheering. Yeah, thank you very much. It was very interesting. And I think your work in RoboRace and yeah, the Indy Autonomous Challenge shows how to bring that on the real car. So I make Rodrigo now the host, and then Rodrigo is able to share his screen. Hi, Rodrigo.
I can.
Yeah, you're the host now. We can see you, we can hear you, and you can now share your screen.
I'm going to share the screen in a second.
We can't see your screen yet.
Yes, I'm sharing it.
Right, now we can see it. Awesome. Okay, the stage is yours.
Okay. So good morning, everyone. I am Rodrigo Senofieni, and I'm a PhD student at Politecnico in Milano. And today I'm going to present my research about the generation of a safe drivable area for path planning algorithms of autonomous vehicles. So before we start, I will do a brief introduction about the problem. So the main objective and the main focus of this of our research was about the online path planning of an autonomous race car. And in our case, the main objective was to replan online a trajectory on a path based on surrounding entities like obstacles to avoid and waypoints to collect. Our algorithm that we developed and we are proposing today has the main goal, of course, of processing all these external entities in order to generate a safe and drivable area that can take into account, of course, these obstacles to avoid and waypoints to collect. Before heading into the definition of the algorithm, I'm going to give a brief explanation of the framework and mathematical definitions. So in a generic race scenario that we are proposing, there are, and we can define some limit trajectories that a vehicle can follow. And these trajectory limits are usually the trajectory that a race vehicle can follow at the limits of handling. So the space of solution that is in between these two trajectory limits define, let's say, a safe space of solution where the path planner can replan its trajectories. So for example, another trajectory that is not feasible is a trajectory that is outside of the trajectory limit. So we can define linear heuristics based on these two trajectory limits that can take into account this safe space of replan region, so that we can make some assumptions on obstacles to avoid and waypoints to collect. We can first define the reachability heuristic as, as the ratio between the curvilinear distance and the lateral shift between ego current position and a waypoint current position. So we say that a waypoint is reachable so that we can collect this specific waypoint if this ratio is greater than the reachability threshold. Similarly, we can also define the avoidability condition, the avoidability heuristic, which is an obstacle is avoidable from a specific waypoint if the ratio between the curvilinear distance between a specific waypoint and the lateral shift with respect to the obstacle is smaller than the avoidability threshold. That means that if a waypoint is inside the cone, the avoidability cone, it means that the waypoint is not safe to be collected because it's too close to the obstacle. In order to not to be over conservative in discarding waypoints that are inside the avoidability cone, we perform an avoidability double check so that we can be sure that the waypoint is safe to collect. So for each waypoint, we check the reachability condition with respect to the minimum avoidance point. So if a waypoint satisfies the reachability condition with respect to a minimum avoidance point of each obstacle, we can say that the waypoint is safe to be collected. After said that, we can show the proposed solution and the method that can generate the safe drivable area. So first of all, we, of course, can process all the entities that are input of our algorithm so that we can take all the waypoints and we perform the reachability and avoidability checks with respect to all obstacles in the current scenario. And we discard all waypoints, for example, waypoint number 3, that does not satisfy the reachability and avoidability double check. After this step, we will have a set of feasible waypoints and we can construct the reachability tree. The reachability tree represents the all possible combination of sequences of waypoints that can be collected starting from ego current position. The weight of each branch of the tree is the reachability ratio, so the curvilinear distance over the lateral shift of the specific waypoint. And the logic in order to select the best branch of the tree is a simple maximum weight, which in practical terms represent the sequence of waypoints that are lowest in terms of lateral shift and curvilinear distance. So this method actually rewards all the waypoints that are the most aligned with the ego current position. And after we selected the best branch based on this logic of the reachability tree, we can construct the safe drivable area in which the path planner will then replan its trajectory. So for each waypoint that is selected in the reachability tree, we will actually apply, first of all, the obstacle inflation process in order to guarantee some safety margin for the planning procedure. And for each waypoint, we will construct the complementary obstacles. By doing so, at the end of each process, we will have a safe drivable area, which will force the path planner algorithm to replan its trajectory based on the logic that we described earlier. And luckily, it will collect all waypoints that we selected. I'm going now to show you some results that we obtained. So we integrated this algorithm in the software stack with the path planner algorithm of an autonomous race car. And we tested our algorithm in a simulation environment with race object scenarios. In this first waypoint scenario, we can see that we placed 3 waypoints to be collected. And according to the logic that I described to you earlier, the algorithms can effectively generate a safe drivable area in which the path planner replans its trajectory in order to collect all 3 waypoints. Another example can be seen in this other scenario in which we placed 3 waypoints. Waypoint number 1 and waypoint number 2 are side by side, which means that they are mutually exclusive. So we cannot collect, we only can collect one of the 2 waypoints. So based on the selection of the highest reward branch of the reachability tree, the final choice will actually be to select waypoint number 2 and number 3 because are the most aligned with the ego current position. So that waypoint number 1 is discarded instead because it's far away from current ego position. Another result can be seen in this mixed scenario. In this case, we placed a mix of waypoints and obstacles to avoid. Waypoint number 3 and number 2 are discarded a priori because they do not satisfy the reachability and avoidability condition with respect to the 2 obstacles. Instead, the waypoint number 1 and waypoint number 4 are considered and the safe drivable area is generated such that the path planner can replan its trajectory and pass throughout both the waypoint. So concluding, the proposed solution is capable of generating a safe drivable area and is capable of pre-processing multiple entities as input, so like obstacles and waypoint. And thanks to the logic of selecting the highest reward path, we can always take the path that has the highest number of waypoints and the lowest in terms of lateral shift and in terms of longitudinal displacement. And currently we are working on making this logic of the reachability and avoidability condition more refined by taking into account a, let's say, more detailed and accurate definition of a simple linear bicycle model in order to have a more defined definition of the reachability and avoidability cones. So thank you. And if you have any question, I'm glad to answer you.
Thank you very much, Rodrigo. That was very nice. It's a shame that you can't be here today. I think everybody would love to talk to you guys about your racing. So you can stop sharing your screen. And now we're having our next in-person talk from Joshua. He's here in person. That's great. Just opening his talk. Share. Yeah, it is. It's not showing the right one. Yeah.
Yeah, that's what I meant. No, but you could just. Do you need this view or? I'm fine without it. Okay. So we can just. There you are.
Cool. Okay, thank you. So hello, everyone. I'm Joshua Spisak. I'm going to be presenting on our modeling and controls for racing on the edge. So how do I click through? Okay, cool. So yeah, I'm with the Biorobotics Lab out of Carnegie Mellon University. My co-author Andrea, who is also here, is with the Air Lab and Data Lab. And mostly what we're going to be talking about is our controls approach for the Indy Autonomous Challenge. So quick background, there were 3 events. The first one was back in June in the simulation race, where we were able to go in speeds of excess of 200 miles an hour and win 4th place. The October 23rd event, we were able to reach speeds of around 70 miles an hour before we had a GPS failure. And then in January at CES this year, we were able to hit speeds up to 140. So yeah, just to give an idea of what that looks like, this is our performance run at 137 miles an hour at the Las Vegas Motor Speedway. And yeah, going to be presenting on how we did that. Cool. So first off, why does this even matter? The reason we like to think about is speeding is a factor in over 25% of fatal crashes per year. A large part of why this is such a risk factor is reduced reaction time and making it more difficult to control the vehicle. The example we have here is actually a spin out we had at 140 miles an hour. And when we started looking at the data, it actually boiled down to the fact that our tires weren't warm enough. So we just did not have enough traction to even make a turn there. So roadmap about what more specifically I'm going to be talking about. Our controls framework shows some evaluation on just tracking the racing line, show evaluation on the lane change task, and then talk a bit about online modeling, motivation for that, and some approaches for that. So our architecture is decomposed into 3 separate tasks: the lateral control, longitudinal control, and gear shifting. All of those collectively get information from some racing line. It could also be from an online planner, for example, as was the case in the Sim Challenge. And we also get an estimate from robot localization that uses information from GPS. Cool. So I'll mostly be focusing on the lateral control, which also has 3 different components. First one is velocity bracketing. Second one is a pure pursuit look ahead. And the third part is just LQR set point tracking. So really the motivation for the velocity bracketing is it's just a mechanism to vary parameters with speed. So for example, changing model assumptions, such as it assumes a fixed velocity. Now we can change the model at a higher level. Also dampening steering, for example, as speed increases, or moving the look ahead further to be more reactive. Speaking a bit more about evaluating the look ahead, really this is just about giving it more of a sense of the future, since LQR is just a set point controller. So rather than just projecting laterally to the path, we then look ahead on the path of fixed distance. And then we take the target and the vehicle pose and just pass that to LQR. So the LQR tracking, a bit about why we chose this particular algorithm. A lot of it comes down to guaranteed fast computation time. It's also very simple, easy to implement, and it also starts to consider dynamic information, which is a huge one. It's not purely geometric or kinematic. So the model we use is the dynamic bicycle model. One of the big things why we think this still works reasonably well is even though it assumes small steering angle, especially on like an ovaloid track, the max steering angle we experience is only about 6 degrees, which is fairly small. And it assumes a constant velocity as well. We could actually reformulate the model to remove that assumption. We chose, however, to instead go with the simpler formulation and then mitigate that with the high-level parameter changing. And so as the lateral controller, it reasons primarily about lateral position and yaw, and then we input steering angle. So I'm gonna skip through some of this, but to actually apply LQR, we take the pose, we take the goal, we formulate a concept of an error state, which is just lateral and yaw error, which we can then minimize using LQR. And this yields a simple feedback matrix K, which we can then apply in the following way. So given the path, form the error state, apply the feedback matrix, and bam, you have steering. So, and then the other thing I wanted to touch on briefly is just the velocity controller, which is very simple as well. It's just a P controller with a feed forward term to account for drag, but it worked for us reasonably well, even at higher speeds. So to talk a bit about our evaluation and how well this actually performed. So we evaluated it on race line following, which is just an optimal race line computed offline. We evaluated it at speeds of around 25 meters a second to 60.5 meters a second. With a maximum cross-track error we experienced was about 1.3 meters with a mean absolute cross-track error of around 42 centimeters. So it's not perfect, but it's still reasonable considering what it is. We can see over here on the plot the velocities we achieved as well as the cross-track error. And then the other evaluation we did was on a lane change maneuver. So you can see in the bottom left plot, we have an outer lane and we have an inside lane. And we formed a path between the two of them and then allowed the vehicle to follow that line using this controller. This was only done at 25 meters a second with the maximum cross-track error of around 55 centimeters and a mean absolute cross-track error of 44. So to talk about some of the advantages of this and why we think this is still a reasonable approach, strong guarantees of fast execution are a big one. It can be run on computationally limited platforms without issue. It's reactive, it's stable, and it's simple. It can be implemented using classical methods. It doesn't take a lot of time, and it works. But talking about disadvantages, because there are definitely some, while it does consider some dynamic information, it's not reasoning about multiple time steps. So it has its point, it's trying to track to it, and it gets the job done, but there's a lot it can't do. Really, it assumes that there's a higher level planner that considers fine information about dynamic feasibility, about acceleration, about curvature limits, and if those break down, then so could this. Fortunately for us, though, we did have a higher level planner that did handle this. So if those assumption holds, this also holds. We are concerned also about how it will extend to road courses moving forward, especially in the Indy Autonomous Challenge. And another big one, which I'm going to talk about briefly, is how it doesn't consider environment changes. So thinking about the limitations and how we want to move forward with our approaches, I'm going to play the spin out video again real quick. So again, just thinking about this, the tires were too cold. Cold tires means less traction. Less traction means less lateral force. And as my co-author likes to say, less force, spinny spin. So how do we actually account for this? Even with model predictive control methods, they're still usually only thinking with a static model. There have been approaches such as with Gaussian process regression, with adaptive controllers, but just thinking about like, what's the best way to handle this? And then another effect we want to talk about is just aerodynamics. So playing this clip here. This is Kyle Kirkwood, and what you're about to see is there's going to be a slipstream there, which causes a disturbance on the front of his vehicle. And he maneuvers very deftly to prevent his car from going out of control. But obviously, this is very risky. So just because of time, not going super into detail, basically the way we want to approach this is starting to incorporate online model learning, think about nominal trajectory, the last controls we sent, vehicle state, and kind of incorporate dynamically adjusting parameters in the model. The big thing which we think that this will help with that hasn't been considered so far is really the aerodynamic effects and thinking about those disturbances in the model more explicitly. Cool. Quick acknowledgement to the MIT-PW team. Lots of people went into making this vehicle deployable. So thank you, everyone.
Thank you, Joshua. I think what we always forget is that the classical approaches, the one we know the best, are the best suitable for such a setup. So thanks again for reminding us that this works. Now we're moving on to our next talk. And I introduce you Yiwei from CMU. I'm sorry, I need to share first. Yeah, the stage is yours.
Hello, everyone. I'm Yiwei from Carnegie Mellon University. So today I will present my work on adaptive safe merging control for heterogeneous autonomous vehicles using parametric control barrier functions. So talking about autonomous driving, usually the first concern will be about safety. So our goal in this work is primarily how to ensure the safety while trying to explore a better way to model the heterogeneous robot interaction. So for the technical objectives of this work, we first place safety as a priority because we want to seek for some provably safety guarantees. And secondly, we want to relax some assumptions on the surrounding robots, which is usually made by some existing works in collision avoidance, like all the others will be fully cooperative. So in this work, we will enable the robot to be able to first observe what the others is doing, estimate the driving behavior pattern of the others, and then interact accordingly. And thirdly, we want to enhance the safe controller's expressivity. So instead of the dummy agent with unchangeable reactions, we want to make more provide more precise safe behavior characterization. Yeah, and talking about our approach, so basically in this framework, we have two modules. The first is the behavior prediction, and second is about parametric CBF-based safe controller. So now we first introduce the second part about the safe controller. So the core technique we use here is called control barrier function. One of the important property is its forward invariance. So basically, it means given a safe set of a state X for a robot, then the control barrier function actually provides a way to constrain the robot motion so that as long as the robot starts inside in this safe set originally, then the CBF will always keep the robot in this safe set and therefore keep it safe. So here's how we define the admissible control space. So that means given a specific state X, as long as we can find such kind of a controller U that satisfies this kind of inequality, then the CBF can always ensure the safety of the vehicle. And the core idea behind our proposed parametric CBF is that it is a new composition of the class K function as a linear combination of higher order polynomials to better characterize the system level safe behaviors while preserving the safety guarantees. So it actually shares the similar intuitions about linear regression. So here's our parametric CBF-based safe controller design. So first of all, we have objective function representing the minimally invasive deviation control from the nominal controller. And the first constraint we have is the actuation constraint. And next, instead of the original CBF formulation, what we have is the parametric CBF, where we basically augment the safety measurement function at H to be a safety measurement vector with higher order more terms with polynomials. So the first advantage of the proposed parametric CBF is that it can provide a richer description information. It can characterize the degree of conservativeness of the system while it's approaching the safety boundaries. And another advantage is that thanks to the special design of the linear combination of the parameter vector alpha and the high order safety measurement vector H, we have real-time computation efficiency so that it can be easily extended to different real-time robotics applications. So next we show how CBF, this idea, the parametric CBF, could be potentially also used in the behavior prediction. So the goal here is we assume there's a vehicle using the same parametric CBF-based controller. How can we use a linear rich regression to estimate the alpha vector used by the other vehicle, which represent the degree of conservativeness or aggressiveness based on the observations? Yeah, so here are some study cases. The first is about how we use a parametric CBF in behavior prediction. So we have the blue card here. It is the prediction object which we are trying to predict its own driving behavior, which is the parameter CBF vector alpha. And we want to make the prediction of the alpha vector based on the observation of like how the prediction object interact with its surrounding vehicles. So we can see that the estimated result of the alpha vector actually has a pretty fast convergence rate towards the grounding truth. And the second application is we show that how could we use such kind of behavior prediction to further improve the performance of the safe control. And the goal here is to show how the parametric CBF CBF prediction can contribute towards more efficient safe control. So here we have the blue car as the prediction object and the red car as the ego vehicle. So basically here we compare the performance with control with the prediction in the loop and without the prediction in the loop. And we can see once we have the prediction in the loop, the task efficiency, the overall task efficiency can be greatly improved and also can reduce the traffic congestion. Yeah, so basically this is a conclusion of our work. We propose a new interaction modeling framework for heterogeneous robot interaction. And secondly, we propose this parametric CBF to provide a richer behavior to better characterize the robot's safe behavior with richer informations. And also we demonstrate how it might be potentially used in the behavior prediction. Yeah. With that, I would like to conclude here. Thanks.
Yeah, thank you very much for this nice talk. And then we are moving on directly with our final presented paper in the session. And we have another person from Switzerland. Thank you very much for traveling that far. And Edoardo is also competing in F110s, which is also great. So I just share the screen and then you're ready to go. All right, the stage is yours.
Thank you very much, Johannes. And so, hello, everybody. I'm here to present you our workshop paper on trajectory conditioned driving for robust autonomous racing reinforcement learning approach from me, Nicolas, Mike, and the senior researcher Michele Magno from the Center of Project-Based Learning at ETH. So we are talking about control for autonomous racing. And okay. Let's just start with a short table of contents. I'll first show the setting and state of the art, and then the reasoning that brought to our novel idea, the trajectory condition for the driver. Then I'll show the setup, the experiments, the results, and then finally conclusion and future perspective. So as it said, control for autonomous racing, we have two main lines of work: model predictive control, and as many of you may know, is optimal when the model is perfectly known, and that is actually almost only in simulation. So often we need to care very much about the model, but it's very successful in many racing situations. And then we have the other line of work of reinforcement learning, which is basically a machine learning technique. So it leverages heuristics, is more human-like, and it also got very promising results in autonomous racing, both in real life and also in simulation. So both these methods, pro and cons. MPC, as I already said, optimal when there is no model mismatch, but when we are doing autonomous racing, there is the huge problem of tire parameters. They are very, very like changing over time, but also non-linear. The whole dynamics of tires is non-linear, and then it's very difficult to tackle this complex model perfectly. And furthermore, MPC is also very computationally expensive. At every time step, we have to solve an optimization program. On the other side, reinforcement learning is computationally very cheap. It's just an inference through a neural network at runtime. It's also a learning heuristic, so you can tackle these complex models in this machine learning way, which is very nice. But it's since it's machine learning, it's black box. It's not optimal. We have no guarantees on its behavior. We don't know what's really happening within these neurons. So we want to use, our idea was to kind of use the pros of reinforcement learning to tackle the cons of this traditional control technique. Specifically, we wanted to focus on being robust to this model mismatch that happens because of tires. And we wanted to do that leveraging the heuristic reinforcement learning capabilities. And then we just wanted it to be also computationally cheap since we were using reinforcement learning. And we have this really nice graphic from the surveys from Johannes and co-authors that shows the previous works that use reinforcement learning for autonomous racing. And most of them in the stack perception planning control kind of substitute the perception planning, either the perception planning with a neural network that generates a trajectory, which is then tracked, or the whole stack. We have end-to-end methods. Those are actually the ones that have best performances. But we want to argue, we'd like to propose a kind of opposite architecture. We want to leverage as much as possible the classic control techniques. Perception and planning, we want them to come from a control background, and then we want to use the reinforcement learning to generate the low-level controls for the car. Specifically, we envision this structure, where we have a high-level trajectory generator. It comes from a more of a control background. Therefore, it generates a safe and known trajectory, which is also race performant. And in our specific case, it's an offline computed trajectory, and we just sample it at runtime. but it can be all kind of optimal trajectory generator. And then at low level, we envision a reinforcement learning agent that heuristically learns to tackle the different tire parameters in our case, but in general, the non-linearity of the system, and will be computationally very fast. Some more details on our reinforcement learning agent. We have the observation space, we have the state of the car, which is position, attitude, yaw, etc. We have the LiDAR scans, and we add the trajectory, which we sample from the global trajectory. On top of that, reward design, for the reward, we have a penalty for constraint violation, i.e. crashes. We have a reward. This delta theta is just a reward for advancement. At every time step, we reward advancement. And then we have, in light blue, our added penalty for swerving away from the trajectory that at the previous time step we fed into the model. Then we have this further down here, the additional training strategies. Very important, the model randomization, the noise, we added noise on the tire parameters during training. And to choose this noise, we use a baseline MPC. And then when this non-learning MPC started not being able, started crashing, we use this kind of boundary parameters that we found, varying them to extract noise for training. So that's exactly one of the two comparison baselines that we chose. Specifically, the MPC is the MPCC from Alex Liniger. And for reinforcement learning, we use end-to-end implementations that achieved state-of-the-art results in many other previous works. Works are cited there. And for all experiments, we use the gym environment of the F110 platform and competition. For some qualitative results, we have here the dotted line is the one achieved by the end-to-end agent when trained the same number of epochs as our proposed TC driver, and we see that it clearly is much more oscillating and uses a much less efficient racing trajectory than the purple one, which is the TC driver, and then we have in gray the MPC trajectory. This is an extract from the training track, and we have the different trajectory, and we see that already here at a qualitative level, leveraging classical control structure helps this reinforcement learning task. But then going on to tire parameter mismatch, the setup of the experiment was that we had a range of training tire parameters, then we took a different distribution for testing, which was mostly outside of training, specifically about more than 60% outside of the training range. And then we let the different baseline and our proposed controller drive on these on the track with this kind of tire parameters. And we can see that our proposed TC driver achieves the lowest crash ratio. It's lowest by a lot than the other end-to-end agent, but also lowest than the non-learning MPC on this kind of track. And but still, performance-wise, it's better than the other reinforcement learning agent, but not than the very optimal and performant MPC. Then we further tested for track generalization, actually, because our kind of structure with the trajectory fed to the reinforcement learning agent is more, we think is more suited. And so here we can see in blue the training track, and the other are the testing tracks. And specifically, we see since there's not really tire mismatch in the testing phase, if we consider the MPC in the overall comparison, we see it's the best performing, never crashes, fastest lap time. But the real comparison is between the two reinforcement learning parameters. Then if we remove the MPC from the comparison, we see the TC driver is the faster, and on average, it's also the best one. At crashes, it achieves around a 3-fold improvement in crashes in general. And we can kind of see these differences in actually the trajectories from three agents. Here on the right, we have the MPC, very precise overall, and follows almost always the same trajectory. And then, but in the center column, we have our proposed TC driver. Specifically down here in this hairpin, we kind of see a racing trajectory that compared to the other end-to-end reinforcement learning driver is much faster and performant than this kind of almost oscillating and very safe in the hairpin trajectory. But also we this kind of new trajectory, this kind of more performance and higher speed trajectory led in this specific case, the TC driver, to more crashes. And finally, of course, as expected, the reinforcement learning agents were like almost 50 times faster than MPC. That was kind of a given. So for conclusion, the main result that we actually wanted to present is the new hierarchical, this new hierarchical traditional plus reinforcement learning controller, which we showed has robustness towards tire mismatch when compared to baseline RL and a non-learning MPC method, has also very good track generalization capabilities, and it's clearly computationally very light. For future perspective, we really want to enhance, we can really enhance the machine learning architecture. We could use recurrent neural networks for adaptivity to different tire and environment changes. We could use a local trajectory instead of an offline computed one, etc. But then clearly most important, we want to try this also on a real race car. So thank you very much.